Assalamualaikum warahmatullahi taala wabarakatuh. Today I'd like to uh, explain to you about the potential flow, which is in the chapter 2 fluid mechanics 2. All right, before we go further, let's review a little bit, and then I give you some introductions on the potential flow. All right, have you seen this picture before? I think this is the famous game for the during during my kids' time, during my time as a kampung boy. So I play these games. We call it the Upeh Pinang race. Okay, if the Upeh Pinang race, if you look at this Upeh Pinang race, and then you see and then this guy run, and then at the same time, pull this Upeh together with him, and then we can see that behind the Upeh, they have one line. So this is the good example actually to explain what is the potential flow, what is the streamline. So the potential flow means that this guy, without this guy, this OP cannot go just static there, and then it cannot move. So this guy become a potential flow. So this guy give a potential, we call it a potential velocity. And then if you look at the back of this UPE, we can see one line, which is this is actually the stream line. So, what we're going to study in this topic, we're going to study these two. One is the potential velocity, and then one is like what is the relation between the potential velocity and the streamline, and then how we can use the potential velocity and the streamline to represent the fluid flow, especially in compressible flow or incompressible fluid. All right, before we start, we should review a little bit the previous class is already studied about the what we call it the conservation of mass. So everybody knows that the conservation of mass is given by these equations, right? These equations represent the conservation of mass, or we can write in other form in the three-dimensional like this. This is a conservation of mass where it's delta U divided by delta X plus delta V divided by delta Y plus delta W divided by delta Z. This is equal to 0. And then in two-dimensional, this is we can write as a du dx plus dv dy. Okay, for this case, for the potential flow, most of the case, and I can say that all of the case, we're going to use this for the whole. We can use this for this potential flow topics. Okay, so in this topic, we're going to use two-dimensional only. Why? Because they have some boundaries. We cannot use a three-dimensional in order to solve the streamline because three-dimensional only exists for the potential flow but not in the streamline. The streamline normally occurs in the two-dimensional. All right, without further ado, and then maybe we can start with the first chapter, which is the first subchapter. We call it the stream function. What is a stream function? So in this definition, the stream function can be defined as mathematical functions in two-dimensional fluid flow which is exists such way that a partial derivatives with respect to the y direction, so partial derivative give the positive velocity in the x direction, and its partial derivative in with respect to the x direction give the negative velocity in the y direction. So the potential velocity normally is given in this equation, which is a psi functions of x and y. This is a string function. The string functions of x and y means that the string functions flow from here, and then this line we call it the line of string function. Then this is functions of x and y, because of at this point we have the value of x value and also y value. So that's why we say that it's functions of x and y. So such that if we differentiate the string functions with respect to the y, we can get the value of u, and then if we differentiate string function with respect to x, we get the negative v, which is already mentioned here, the negative velocity in y direction, which is actually the negative v. Because this also we can return as a like this, okay, del psi del x, this is equal to minus. All right, the conservation of mass, as I mentioned in previous one, the conservation of mass give in two-dimensional. This is in two-dimensional of conservation, for the conservation of mass in two-dimensional. So we have du dx plus dv dy equal to 0. Del u del x plus del u del y equal to 0. So if we substitute value of u here, now we substitute this into this one. So if we differentiate this one, so del L, del y del psi del y plus del y minus del psi del x, this equal to 0. Why? Because of we try to make sure it's similar to this, and then because we want to prove that it satisfies the conservation of mass. So if we solve this one, we get d squared y, d squared psi divided by dx dy minus d squared psi dy dx equal to 0. Therefore, we can conclude here that these equations are satisfy the conservation of mass. Okay, the exact differential of this psi. So if d psi equal to del psi del x plus multiplied by del y del x dx, so plus del psi del y multiplied by dy. So if we know that this is a del, we know that the del y is given by this, del psi is given by this equation. So del psi equal to minus v del dx plus u dy. So because of we substitute back these equations, all right, from this equation we substitute into this one, so we get these equations. Okay. So del psi minus v dx plus u dy. So if del psi equal to 0, del psi equal to 0, if we say that these equations equal to 0, so we simplify this one, what we get actually u dx equal to v dx equal to u dy. So if this one 0, so what we have from here is u dy equal to v dx, which is a similar like this. So now if we simplify this one, we got the v dy equal to u dx. In the previous lecture, we write this as a like this. We say that dy dx equal to u over y. Sorry, u over v. U over v. If you still remember in the previous lecture, this is equal to, we call it this as equations. Equations stream function. Okay, if you still remember, this equation is called it the equation of stream function, where you have this line. I already explained in the previous lecture. If we have a string line like this, and then we have this velocity. So if we differentiate this one, this is the y, this is the x, and then we have the u here, and then v here. So from these equations, you can get this one dy dx equal to, sorry, dy dx equal to v dy. Okay, this is a mistake here. I make a mistake here. So this is not this one. So mistake here. This is the v. v. Alright. So if that was the case, we can say that along this line, the string function along the string line, the string functions are constant. What it mean by constant here, which is if we measure here, this is we call it the psi a. So take a value here, psi to b, and value here, psi to c. So in this case, psi to a equal to psi to b equal to psi to c. Okay, right. So this is string function which is constant along the streamline. All right, now next we go to the velocity. We go to the next, which is when we have the flow. When we have the flow, I take the example. We have the flow inside the pipe. So we have a lot of streamline here. Okay, the flow can flow when we have the flow rate. So when this is a flow, we call it this is a flow rate. Okay. So when the flow gone through this flow, so which is the we call it the dq. Dq is the change of flow rate. We have one here. We have psi, and then the next string function or the next string line. This is string SL1, SL2, and then this is SL1. So in between the SL1 SL2, the flows goes through in this surface, this area. So we have the dq. So and then out in this one and in this one. This is means like this. If you studied before this in the conservation of mass, so what we have, for example, if we put here as a q1, and then this one is a q2, and then here is q3. So the flow come here and goes here, and then also goes here. So similar in this case, it goes out in this way, and also goes out in this way, and then in from this one. So if we do that, the dq is a u multiplied by the area. So per unit depth, so we call it the dq into u dy. U dy means that in this area, velocity flow rate in this area, and then minus v dx, which is flow rate in this area. So if we look at this is u. We can replace by this equation, which is we have studied before. We know that du equal to d psi dx dy del y dy del psi del x dy, and then we have del psi del x del y dy, and then we have del psi del x dx. So we replace these two equations back, and then if we simplify here, we know this is del psi del y dy. So what we have here is the half or derivative of this plus derivative of this is equal to the change. All right, so dq actually equal to del psi. So now we can integrate this one. So we have del q equal to del psi. So now we integrate this one. Is bounding from 1 to 2. From 1 to 2 mean that from the string function line 1 to the string functions line 2. Sorry, string line 1, string line 2. So we have this equation. So if we simplify this one, we got this. Q12 equal to psi 2 minus psi 1. Okay, this is how we calculate the uh, flow rates in between two streamline. All right, now the difference between this value of the the difference between value of this the flow rate is we call it the flow rate per unit depth. Okay, we finished the first part of this lecture. Uh, Maybe we will continue to the next one after this. Okay, you can see my example in my other videos, which is I already explained the detail about this example. Okay, thank you. We go to the next topic.